Okay, my name is Danica Fine, and we're going to talk about some Kafka-based data pipelines here. Just give me one sec to make sure everything is up. All right, but before we get into that, I want to know how many of you picked up some crazy hobbies over the last year, or immersed yourself in things that you just way too deep, right? Okay, I feel like some of you are lying, all right, and I'm just going to move on. I'm going to pretend like everyone said yes because it's probably true. You can't hear me? No? Oh, really close. Oh, man. Okay. Anyway, well, okay, I'll ask that again. How many of you have weird hobbies from the last 2 years? Okay. Yeah, more of you answered. Great. How did those go? Right? Things got a little weird. I have a hobby. It got really weird. I have a lot of houseplants, and that's not even all of them. Probably like 40 plants. It's a jungle. My boyfriend hates me sometimes. But yeah, this really got out of hand, especially when I considered that I was spending more time checking on my plants every day than I was actually, I don't know, working, doing things that I probably should be paid to do, feeding myself, whatever. And I also realized that I'm just a bad plant mom sometimes. So this is a problem, right? I feel like I need something to help me, right? And I'm an engineer, so I could build something to help me and probably spend way too much time doing that, So I asked myself, is there a better way? Which really was a silly question because of course there's a better way. I could buy some plant monitors, obviously. So that's the wrong question. The real question is there a more interesting way, right? And as an engineer, yes, of course there's a more interesting way. I have the technology and probably the willpower and way too much time, and I can also build a pretty cool plant monitoring system, all right? And this was my excuse to get a Raspberry Pi and finally build out that hardware project that I wanted to build out, right? So yeah, this is my first hardware project, and I had way too much fun, and this is just the beginning. So there will be a lot more of these talks. I'm just gonna keep going. All right, so I asked myself, how could I build a plant monitoring system? This is a super, super high level, scratch pad of the design. I needed something to monitor my plants and let me know when to water them. I didn't want to get into, automating the entire system. I rent, so I feel like that would be a bad idea. So I just wanted something to monitor my plants at the very least. So the system that I envisioned was pretty simple. I'd get some soil moisture sensors, put those in some plants, take those readings regularly, and then I would enrich those readings with some metadata, obviously, like, I don't know, how much water does that plant need, and what is that plant's name while I'm at it? So I'd add some of those bits in, throw it into a black box, and at the end I'd get some sort of alert, right? So this is a very, very high-level view of what I wanted to do, and so from there I fleshed it out a little bit. Zero indexed, just so you guys didn't get lost. So I'd start with that metadata. So like I said, what are the moisture levels that every plant needs? What are these plants? Where is it? I don't know, when did I get it? So I'd have that information, and I wanted to put it in Kafka. I work for Confluent, so I really love Kafka. Okay, we'll get into that later, but I wanted to use Kafka as sort of the backbone of this whole project. Okay, so I had that metadata. I then, set up my Raspberry Pi with my moisture sensors and capture these soil readings every so often. From there, I'd use some sort of stream processing, right? So I'm getting these real-time readings from my plants, and I need to combine that with the metadata, get some answers, right, and start acting on it. And then at the end, I could send some alerts to my phone, hopefully. That's what I wanted to do. And I learned that I could be using that with a Telegram bot, which is pretty cool. I don't know if you all use Telegram, but it's pretty awesome. So we'll get into that a little bit more, but knowing this high-level workflow, what I wanted to do with it, I could then buy some hardware. The best part. This Raspberry Pi, absolutely overkill, but this is the only thing I could buy at the time. If any of you got into hardware projects for the last 2 years, you know that there was a very, very limited inventory, so yes, overkill. It's the only one I could find. I also got this half-size breadboard, which came for free with what I ordered, which really worked out well because I actually needed it. I had no idea going into that. I chose these capacitive moisture sensors. They're I2C. If we want to get into this later, feel free to come up to me and I will explain why I chose these ones. But they're pretty affordable and relatively high quality for what they were compared to everything else. So bought a couple of those. And beyond that, I opted to crimp and cut all of my own wires. Mostly for fun, I guess. I had a couple days, so I purchased some JST connectors, dusted off the crimpers in the garage. Why did I have those? I don't know. And yeah, I ended up using a couple meters of wire, so that was pretty great. Also a key thing is the plants that I'm monitoring. So these were the unwilling participants. They had no idea what was coming at them. I chose these particular plants in a very scientific way. They were really close together, and there was an outlet behind them. So made it a little easy for myself. So with the hardware in place, and I decided the plants I was going to use, I could actually start putting this together, right? And I'm going to do some hand waving here in the interest of time. So if you have more questions afterwards, please. This isn't a hardware conference, so maybe at my mechanical engineering talk we'll get more into this. But yes, suffice it to say, there was a lot of crimping, a lot of soldering. Got into that. That was cool. Maybe a little bit of tears, but what good project doesn't involve that? And in the end, I ended up with something cool like this. Please don't judge my soldering. In the end, I had four moisture sensors connecting these plants. 4 seems like a low number, but I'll talk about that more. These are all wired through the breadboard, in turn going into the Raspberry Pi. And all the sensors, like I said, are I2C, so they're all communicating via unique address and had to use the same input channels, so hence the breadboard. And I'm going to move on before you look too closely. Great. So on the software side of things, Python 3.7. I used pip, because I had it, sorry, to install the Confluent Kafka library. I know, how dare I use the tools I have. And then it's also worth noting that I was leveraging Confluent Cloud for my Kafka cluster, which we'll get into. And I'll be doing the stream processing on there with ksqlDB. But on that note, what even is Kafka, okay? If you attended my colleague Dave Klein's talk yesterday, you got a pretty quick Kafka primer, but I want to flesh it out a little bit more and make sure everyone's on the same page. So Kafka is a distributed event streaming platform. That's a pretty concise, short sentence, but let's unpack it. There's a lot of words in there. First of all, what are events, all right? Events are pieces of information that indicate that something has happened. It's pretty simple. Ideally, an event, when we're dealing it in the context of Kafka, is the smallest amount of data without excess that you can use to completely describe that something that has happened, all right? So we need some sort of when, we need a who and a what, flesh this out and decide what happened then. Events are a pretty efficient way to describe things that are happening throughout your whole system. So Kafka is a really great way to re-architect your entire architecture, I'm just saying. And this is due to the fact that events are immutable, all right? If you're a purist and you like functional programming, I grew up on OCaml, so if you like if you like functional programming, this is entirely intuitive, right? The fact that events are immutable. Events describe things that have happened, and barring weird things like you getting a time machine, you can't really change that, right? So you understand what events are, but I still kind of haven't told you what Kafka is. So again, it's a distributed event streaming platform. So a Kafka cluster consists of multiple broker nodes. These can be bare metal, VMs, containers, however you want to run it, wherever you want to run it. And the primary unit of storage in Kafka is called a topic. And these topics are further broken down into smaller components called partitions. These partitions are actually themselves immutable append-only logs, where these individual events that we talked about live. They're stored there. We produce data into Kafka as key value pairs, and we use separate clients called Kafka producers to do that. We can have as many producers as we want, writing to as many topics as we want across the Kafka cluster. Once the data is in Kafka, from there it gets a little more interesting. We can start reading data and consuming it from a Kafka topic using another separate client called a Kafka consumer. And again, we can have as many consumers as we want, consuming from as many Kafka topics as we want, but we can take it a step further, and these consumers can sort of share the processing load of consuming from a single topic, or they can consume independently from the beginning of the topic whenever they want. And that's a really important thing in Kafka. A Kafka topic is not a messaging queue. Unlike other sort of event platforms, when data is consumed from a Kafka topic, it doesn't disappear. And it's a log. A topic's a log, right? And when you yourself read application logs, what happens when you read a line? Nothing. It stays there, all right? So anyone else can come through and read that log from start to finish, and they're going to get exactly the same information that you got, right? So the same thing is true of a Kafka topic. These messages are free to be read by as many consumers as you want, and the messages don't disappear. The consumers are fully decoupled from the producers. That's also important. Hmm? It is awesome. Thank you. But where does Confluent come in? All right. Confluent offers Kafka fully managed in the cloud. So it's pretty great for these sorts of projects where you want to use Kafka, but you don't want to set up any of the infrastructure. I had enough trouble setting up my actual hardware, let alone running the infrastructure behind the scenes. And on top of that, Confluent has some great tools built in to help you integrate with external systems. So there's tools to bring data from sources into Kafka and then move data from Kafka out into sinks. And then there's also some great stream processing tools, which we'll get into later. But back to the project at hand. Before embarking on any sort of data-related journey, the first thing I tell anyone is to think about the data you're using, all right? You really need to understand the data sets that you're getting into. So I really recommend taking a step back, thinking about these, and if you are the producer of the data, if you're creating it, definitely create a schema, all right? It's gonna save you a lot of trouble later on. And as you build out a schema, you're gonna start thinking more deeply about the information that you're working with, and you're gonna understand your data set better and really get a feel for what you need for your project. So beyond that, schemas are just great for making sure that downstream systems get the information that they think they're gonna get. So if you're working in industry, I recommend using them. So in my case, I defined 2 Avro schemas, one for that houseplant sort of metadata, like the information on the plant itself. I gave all my plants names, so I figured that would be fun to be in there. I also had the threshold for moisture that my plants would be anticipating, the lower threshold, and also information on temperature and what have you. Then on the other side of things, the other schema, I have the readings information. So the time that we're actually taking this reading, the temperature that is at, the current moisture level, everything that we're getting from those sensors. And both data sets here had a plant identification number to help me keep track of the plants and serve as a key later on. All right, so I've defined my schema. I understand what data I'm working with, so let's actually put it into Kafka. So I created a couple Python scripts using that Confluent Kafka library to make this happen, and actually all the programming for this happened in Python. So coming from a Java background, this is so satisfying. This is so nice. In the end, I was using 4 sensors, and I mentioned that earlier. So that seems like a very small number of sensors, given the number of houseplants I have. This is actually a hardware limitation. There's only so many I2C addresses that I could give to the sensors. It had a couple switches on the back that I could flip, but in the end, I can only use 4. To take it a step further, that might be another phase of the project. I can add some more. So I had these 4 plants that I was monitoring, and I set up a mapping between the IDs of those plants and the I2C addresses, and basically just had a loop going every 5 seconds. I could grab that temperature and moisture value and serialize it with Avro, push it into the Kafka topic. From the plant metadata side of things, again, I only had 4 plants that I was currently monitoring, small amount of data. I also wrote an additional script to take that metadata and push it into Kafka, but kind of overkill because I only had 4 rows going in there for now. But all right, the data is in Kafka. How do we actually go about processing it? There are a couple ways to do this. I really love showing this visual because I think it gives a good idea of the options that you have as far as processing with Kafka. The OG way to do this is to use the consumer producer API there at the bottom. And you'll see here that there's this scale of ease of use and flexibility, okay? So at the very bottom, the lowest level option is just that consumer producer API. It's available in your favorite languages, Python. I have a link at the end for you. But that said, it's a little more difficult to use because you are, like I said, it's that lowest level option. If you're using this for stream processing, you have to actually go through the process of consuming the data from Kafka, doing any sort of transformations in memory, managing your own state, and then pushing it back up to Kafka at the end. So it's a little more hands-on. So if you want to, if you're a sane person, you're probably going to use one of the other 2. So moving up in ease of use is Kafka Streams. And you see here some of the API that's available to you, the filtering, aggregations. Basically what Kafka Streams does for you is that it takes that hassle of managing state off of your hands. So Kafka Streams is a Scala Java-based library that offers all of these transformations out of the box for you. You get some cool things for free, like scalability. I said that you can sort of consume information in parallel with vanilla consumers, and you get the scalability for free because it's built on top of the consumer and producer API. I said that this is a JVM library, but there are a lot of Python-friendly options available to you. Some wrappers. I think the most popular one is called Faust. We like those sort of references in Kafka. And then the easiest way to conduct stream processing with Kafka is with ksqlDB. And this is something that is available to you as part of Confluent Cloud. So in addition to getting your fully managed Kafka cluster, you also have that built-in stream processing capability. But ksqlDB is super cool because it's just SQL. It's SQL syntax. You see a little bit of it up there. And you have access to all this powerful stream processing. You can spin up streaming applications pretty easily just by writing a little bit of SQL. So that's what I choose to do here. I didn't want to actually run anything on my own. I like that I can leverage it through the cloud, and yeah, not manage anything on my own side of things. So we're going to jump into ksqlDB now. There are two main constructs in ksqlDB: streams and tables. And remember, it is a SQL-like language, so I'm going to go into that, but keep that in mind. Streams represent unbounded ongoing events, right? And tables, on the other hand, show the current state for a given key, or whatever keys are currently in the underlying Kafka topic. I'm going to use both of these as we move forward to represent both the plant's metadata and also the readings that we're going to dive into. So this is a sample of ksqlDB code. And we are using this to create the table that is backed by the metadata topic. I chose to use a table here because if I ever wanted to update the value for the metadata, I'd want my stream processing application to leverage that most recent data, right? That's more important here. And again, this syntax should feel very familiar as it's basically SQL. And also, the underlying topic is formatted as Avro. Remember, we created that Avro schema. So the really cool thing about defining it as Avro is that ksqlDB, as a consumer of that Kafka topic, can get all of that field and type value on its own, right? The only thing I have to define, because this is a table, I have to define the key, which value we're actually using as the key. Every other field is pulled in for free without me making some weird spelling mistakes. I think that's the biggest set of errors that I encounter when I use any programming, really. So to create this table, we just point to the Kafka topic, tell it what format we're pulling it in as, and define the key, and we can move on our merry way. And this is what the ksqlDB editor looks like in the cloud. You just copy and paste any sort of SQL, you can write it here, run it, and it'll go ahead and create that table and your streaming application behind the scenes. From there, I could create the actual stream of data for my Houseplant readings, the stream that's coming in. Again, it is Avro data, so we don't have to specify any of the fields or their types. I just point to the topic, tell it's Avro, and again, just run this through the cloud, and it will start bringing in that stream. And then from there, I needed to combine these two data sets, right? Conduct some stream enrichment, right? So I had that ongoing stream of readings, and yeah, I can determine that some plant needs to be watered from that, but what I really need is the metadata information to actually make sense of it, all right? So to enrich this data, I am conducting a stream to table join, and this should feel familiar, just like a regular SQL inner join, okay? And I'm using an inner join because I want to make sure that the output of this query, the output of this stream processing, has all the information that I actually need. So I need that metadata as well as the readings information to actually make sense of the information that's going through this application now. So to do this, again, we point to the topic that we're going to feed this into. We tell it I want it to be Avro again, and then we just do a simple select and join. Very, very similar to SQL. But you'll notice that I have this extra bit at the bottom with the emit changes. And this is a phrase that indicates that we're creating a push query. So what this means is that the result set, the result of this stream processing stage, will be an open-ended stream of data that's pushed to me as output, okay? It's going to be ongoing. Every time a new piece of information arrives on the underlying Kafka topic going into this, we will get some sort of result, as long as the join succeeds. And this is contrasted with a bounded pull query. This is another option available to you as part of ksqlDB, where I would be pulling a finite result set that reflects the current state of the underlying stream, all right? So in order to get a constant flow of data, we want it to be a push query. And now that I had all the information, I had a stream of data with all the information that I actually needed. I have it enriched. It's all there, ready to go. I can start to make sense of it. So I had to revisit the overall goal of this project at this point. So whenever a given plant has enough low moisture readings, meaning that, that it needs to be watered, I want to send an alert. I would like to receive some sort of notification. But how do I determine how to send that alert, and how often do I send them? I decided that I didn't want to inundate my phone with alerts every time I got a low reading. That would just be ridiculous, and we're taking them every 5 seconds, so that would be a little too much, especially when I'm traveling and maybe just running errands. I figured that receiving an alert a couple times every day would give me enough time to act on this and water my plants. So I opted for a 12-hour notification window. I also noticed that my sensors weren't perfect. If you've done any hardware projects, you've probably learned this, that they're not actually giving you all the data exactly as you want it. So sometimes I get false low readings or false high readings. But the general trend over time would be that the moisture percentage would decrease. So within a given 12-hour period, I decided that it would be good enough that if I received an hour's worth of low readings, that's enough to indicate that, okay, this is a real amount of low readings, I should probably water the plant. So the readings, again, being taken every 5 seconds, that would mean I'd need 720 low readings, in order to send an alert. So this is the query that I wrote to achieve this stream processing. So I wanted to receive an alert every 12 hours, so I set up a tumbling window, non-overlapping 12-hour windows. And I specifically, you see here, count the rows where the moisture value on the readings is lower than the lower moisture threshold that's contained in the metadata topic, or that had been contained in the metadata topic. And I specifically want to output a result when the count of those rows reaches 720. And this might seem a little wonky, so let me explain a bit more. Whenever we're windowing and conducting an aggregate, the output is a table where each row is computed per key per window, okay? And this makes sense because a table provides the latest value per key. But the query is operating over the full space of records, right? Every time a record is produced to Kafka, it's going to flow through here. So there's an underlying state, right? In order to conduct this sort of count, there's a state. So every time a record goes through, if it satisfies that filter, it will be added as part of that aggregate. So the bottom line is that rows 1 through 719, as this state is updated, they're not going to output anything. As soon as we get to 720, it will output a row. So we're going to receive 1 alert per plant per 12-hour window, which is exactly what I wanted. All right. From there, I had these messages in Kafka. I knew, when I should actually be alerting. All I need to do was move the data out of Kafka and actually give it to me, right? So I set up a Telegram bot. Anyone can do this. It's like, it takes 2 minutes to set up a bot and just start playing around on Telegram. And what's convenient about it is that it has a chat API so that you can leverage the conversation you're having with your bot and directly use that endpoint to feed a message to your phone, which is pretty cool. To do this, I leverage a tool called Kafka Connect. This is an auxiliary Kafka tool that's available through Confluent Cloud to move data from Kafka out of the ecosystem. All right, so I'm using the HTTP sync connector. You point to a specific endpoint, and it will push data that way. It's fully managed in the cloud. You don't actually do any coding. It's pretty great. And then to get my sync connector up and running, I said it was no code, but this is the sort of output configuration that is generated as part of that connector. So you here see some basic information. It points to the topic that we're actually using, pulling that data from, the format that we're using. You specify a key to actually access your cluster, an API key. This is the actual API URL that we're pushing it to with my chat ID. And I'm using regex to actually go in, fetch the underlying message, the relevant information, and I'm pushing that to the text body of the message that's going to the API. That's the alert that I get on my phone now. They all have names, so Bradley was dry. And yeah, like I said, that this was my first hardware-based project. I'm now inspired. I'm going to make so many more of these. I'm really excited about Raspberry Pi now. I've already purchased a bunch more sensors. I'm ready. So if you are looking to play around with this, this is such a rewarding project for me because I didn't have to set up any infrastructure, and I got to leverage stream processing the whole way. So on the left here, we have our Confluent developer Python resources, everything about the Python client. And on the right, I have my GitHub repo with all of the scripts that I used and some of the configuration files to set up the project. Cool. And now I'll leave that up. But if anyone has any questions, I'm happy to answer them now. Yes, ksqlDB is running exclusively through Confluent Cloud. What's running on the Raspberry Pi, and this is why it was complete overkill for the 8 gig Raspberry Pi, it's running 2 Python scripts to grab those readings. Yeah, if that, yeah. It's pretty simple. This is, yeah. I know, it's so cool. Like that was gonna be the most difficult part of the pipeline, I think, is moving it and actually giving it to my phone. But yeah, the Telegram API made it so easy, so simple. Yeah? I'm sorry? The plants are okay. They are all right. They haven't complained, thankfully. But yeah, nothing so dramatic as that first picture. That has not happened recently. But yeah, I am already planning. As soon as I can get my hands on a Pi Zero, I'm going to set up a lot more plant stations to monitor my plants. So there'll be way too many of these in my house by the end of it. Yeah, automate the watering. Okay. Again, I said I rent. None of my plants actually are near a watering source, and I cannot bring myself to set up a bunch of tubing or reservoirs. I don't know. It seems like way too complicated at that point. Yeah, I want it to be automated like that, but we'll see. Let's see. The next step that I want to do is have little monitors next to the plants, so they just have like Tamagotchi style, like they just put sad faces on when they need to be watered. And then that way, when I'm gone, my boyfriend can just water them, right? It won't happen. No. Maybe I'll just make them cry at that point. Yes? Yeah, that's true. Yeah, I've gone back to the drawing board as far as how I'm gonna do this. My partner is a mechanical engineer, so I'm like, you're gonna figure this out. We'll build something. Anyone else? Cool. Thank you so much. Happy to be here, and